All right, so section 9.3b, P-series test for convergence, which also includes harmonic series. Let me give you the definition of the P-series really quick. So P-series, this is one of those functions or series, that it's going to be kind of obvious that it's a P-series, that you're going to see right now what it looks like. We're going to say the sum as n goes from 1 to infinity of 1 over n to the p. Some people will call the P series the power series, but that's actually not a good name to call it, because we actually do have something called the power series. That's not exactly this, but they just say, oh, well, P is the power, so that's what they're talking about with the P series, okay? So something like this is called a P series. If you were to write the first couple of numbers, it'd be like 1 over 1 to the P plus 1 over 2 to the P plus 1 over 3 to the P, etc. So this is called a P series. Okay. And they say where P is a positive constant. So notice it doesn't have to be an integer, positive integer. It could just be something positive. It could be a fraction. So n to the 3 halves. That's okay. You can have 1 over n to the 3 halves. It's a positive and it's a constant. So you can have 1 over n to the pi, because pi is not a constant. It's ever changing, right? But anything like that is a constant should be good. Now, they also give us the harmonic series too. And right now we'll talk about how you can check for convergence. But the harmonic series is basically just the P series. It looks like this. The sum as n goes from 1 to infinity of 1 over n. Okay? And they're going to say, note, P equals 1. Okay, so the harmonic series is just 1 over n. Okay, so it's still just a P series, but a very specific P series. If P equals 1, then we call it a harmonic series. Okay, so there is a formula. Remember I told you guys that there's a, if you're a musician, you know, that they always tell you that there's numbers everywhere, right, in music and everything like that. I mean, it's obvious with music, you have to count beats and stuff like that. But in order to find a harmonic tone, so I can put right here, just as a FYI, general harmonic tone. In music, we actually use this formula for it. That's what we use. To find any general harmonic tone, you can use that formula to figure that out. Okay, there's a lot more work that goes into it, but I'm just saying this is kind of what they found out, that this is how you can find some of your most general harmonics. So you know, Pythagoras is known for saying, you know, all his numbers, right? And it's kind of true. I mean, numbers are everywhere. Everything can be represented numerically, pretty much. Just you may not know the formulas, but they're out there. They're out there. Pythagoras was also one who, before you entered his classroom, there was a saying on top of the door that said, "Let no one who doesn't know geometry enter this hall." So in other words, if you had no idea what geometry was, you weren't allowed, right? So he was also known for saying that. It kind of mean, like, he wouldn't allow people to come in and learn. Like, you had to kind of know it, right? So anyway, we have two formulas right here, a P series and a harmonic series, right? So just to talk about how you can tell if something is convergent, right? So how are we going to figure out if one of these things is convergent? So let's talk about the convergence of a P series. Now, whenever I say P series, that does include harmonic series as well, because a harmonic series is a P series. It's just a specific one when P equals 1. Okay, so how do we check if something will converge for a p-series. So we're going to say this. For the p-series, the sum as n goes from 1 to infinity of 1 over n to the p. 1, it converges. And by the way, this is a really easy test. If p is greater than 1. 2, it diverges if p is less than or equal to 1. It should be greater than 0, by the way, so let me actually put that in there. But they do say it's a positive constant, so that's kind of like a given. Okay, so if p is less than or equal to 1, then we say it diverges. If p is greater than 1, then we say it converges. So you can see why this would be considered an easy test. You're just checking for the power. What would you say about the harmonic series? Would the harmonic series converge or diverge? Diverge, right? So that's something you guys should memorize like right away, okay? The harmonic series always diverges. Now, eventually, when we get to alternating series, there's going to be a form of a harmonic series that's there, and a lot of times people get that answer wrong when I say, okay, look at this alternating series that looks like a harmonic series. What is it? And they always say diverges because they remember harmonic series always diverges. But yeah, eventually there's going to be one that looks like this. Okay, and they're going to say that diverges because 1 over n is a p-series, the p is equal to 1, therefore it diverges. But then you see how there's this minus plus thing that's happening right there, right? That function actually does converge. Okay, so sometimes we misapply the definition. But notice this series that I gave you right now, that is not the harmonic series. This is not the harmonic series. This little piece is, but not including the negative 1 to the n. That's actually called an alternating series. All right, so later on you'll probably experience that situation and you might actually make the same mistake. Maybe you won't. But yeah, that kind of happens right there. But for now, just look at the power. If it's greater than 1, it converges. If it's less than 1, it's going to diverge. So unfortunately, I jumped the gun here. So let me see. Do these converge? Or diverge? All right, so let's do this right here. A, and like I said, unfortunately, I jumped the gun on this one. I apologize, but the first question was supposed to be this. Okay. So we just covered that, right? That is a p-series. The power on the n is a 1. Okay, so I'm just going to put note p equals 1, right? So we can say that this diverges. So sometimes you don't really have to do much work. You just have to kind of notice it. And once you notice it, that's it. You're good. Okay, now other times there might be more work that you have to do. Thankfully it's not part B, but I think it is part C. What about that one? That one converges, right? P is equal to 3. And if P is greater than 1, then it's going to converge. So I'm going to say this converges. Easy enough so far? Right? You're just looking, right? You're observing, and whatever you observe, you're going to give me an answer. Now, this next problem is a little different. Okay? But don't worry, this is not a p-series, okay? Because I just said the instructions were, do these converge or diverge? I didn't say anything about, whoa, what's going on there? I didn't say anything about this being a p-series for all of them, so I don't know what's going on there. I hope it doesn't keep doing it. I may have to restart my computer after this. So the sum as n goes from 2 to infinity of 1 over n ln of n. So notice you can't do this using a p-series test. Okay? You can't do this when using a p-series test because it's not just 1 over n to some power. I mean, there's other stuff down at the bottom. So what you're going to have to do is most likely an integral test because that's what we've been learning in this section, right? So what you would want to do is probably graph this thing just to kind of check it. Let me see if I can actually bring that up really quick. I don't know why I need that. Give me a second. I don't know why this thing's doing what it's doing. Well, the function here is 1 divided by x ln of x, right? So ln would be, where's my ln at? This button here. Now, I know this is kind of short, but so let me zoom in just a little bit. Remember, we're starting at 2, so I'm going to move my cursor to about 2. So I'm just kind of moving it a little bit. I'm at 1.27, so I'm just going to zoom in there. So notice at 2, okay? You guys can see the 2 value right there. This, okay, right here, okay? That right there is the 2 value. Now, is it a positive value right from there? Yeah, and it's never going to go under 0, right? It's kind of cresting. It's not going to go under the x-axis. So it is positive, it is decreasing, and it is continuous from 2 on. So that means I can use an integral test for this. Okay? I can use an integral test. So I'm going to try that. So I'm going to basically let f of x just be 1 over x ln of x. And I'm going to integrate this from 2 to infinity. Now, with this, I have to fix the fact that I have an infinity up there. So limit as b goes to infinity of 2 to b of 1 over x ln of x dx. And then I start to integrate, but I can use a u substitution. I'm going to let u equal ln of x because du would be 1 over x dx, which is right here. 1 over x dx, that's that. So let me go ahead and rewrite this. So this is the limit as b approaches infinity of the integral of 1 over u du, because ln of x is in the bottom. Now the integral of that, limit as b goes to infinity of ln of the absolute value of u plus c. But now I get to put back in my limits. So limit as b goes to infinity of ln of absolute value of u from 2 to b. Now remember, I forgot to put my u value, I'm sorry. Yeah, ln of x. So it's ln of the absolute value of ln of x. Well, that's nothing. Just you find the ln of one thing, it's going to give you a number, then you take ln of that number. So it's like saying sine of 45 degrees, right?
Why don't you carry the B and the 2 like throughout the whole time?
The reason why is because when I substitute it in for u, it doesn't mean that my upper and lower bounds stay the same for that u value. Right now, when I'm done with this section, if I do have a little bit of time, which I might, I'll show you an example of why we don't do it. Okay, you have to choose whether you want to do it or you don't want to carry it. I always leave it out, and I only, so you'll notice when everything was still with x's, I kept the 2 and the b's there, right? As soon as I change it to a u, they disappear for me. And then once I put the x back in, I bring them back in, right? And that's because they have different values once you do your u substitution. But I'll show you something like this right now. So let's go ahead and do this right here just to finish off. So limit as b goes to infinity of ln of b minus ln of 2. So if I plug in infinity for this, what do I get? It should be infinity minus some number, right? Which is just infinite. So what do we say about this function? Yeah, so since, I should write that a little different. Since the integral from 2 to infinity of 1 over x ln of x dx diverges, then the series as n goes from 2 to infinity of 1 over n ln of n also must diverge. So remember, that's the definition of the integral test. What one does, the other must do, right? So if you know that the series diverges, then you can assume that the integral will diverge. If you know the integral is going to diverge, you can assume the series is going to diverge, right? So it just kind of depends on that. So I'll give you guys the homework for this in a bit, okay? I'll put it in the video, but let me just explain something really quick for you guys. But that's it for this lesson. Now let me just go over something a little different here. Let's try like the integral from 1 to 2 of x over x squared plus 1 dx. Okay, so this is going to be towards your question of why do we not carry the 1 and 2, let's say, in this problem, right? So this is what's going to happen. You can't integrate this unless you do a u substitution, right? So let u equal x squared plus 1, so du would be 2x dx, so half du would be x dx. So when I go through and I substitute, I get half integral du, and then the x dx is going to be replaced with that du there. The bottom's going to become a 1 over u. Now, if you want limits to show up, and I don't know why that's happening, I'm going to have to restart everything here. If you want the limits to show up, then what you have to do is recalculate them. Yes. So if you want to know what your new lower bound is, then you have to put it in there. So get your 1 and plug it in where it says x squared plus 1. So x squared plus 1, if you plug in a 1, becomes 2, right? So this would be 2. And now get your 2 and plug it in. So 2 squared is 4, 4 plus 1 is 5. So now you can actually keep your new limits with your substitution, because those upper and lower bounds do not represent 1 over u. They represent x over x squared plus 1, right? So if you want to do it that way, that's fine. And you notice when you do this problem, half, this will be ln absolute value of u from 2 to 5. Notice you're just going to have ln of 5 minus ln of 2, or if you want 1 half ln of 5 halves, or you could actually have this. Okay, but either way you do it, you're going to get the same answer. It's not going to matter. So I always do it the other way because I don't want to mess up in my calculation of my new limits. What if I add something wrong? What if I forget to put a plus 1 at the end, or I forget to square something while I'm recalculating my new numbers, and now all of a sudden my answer is incorrect because of the fact that I decided I was going to change my upper and lower bounds as well. So for me, it's always play it safe. Don't include the numbers until later. They already did them for us. Why am I going to redo them, right? So I always play it safe.
On the A/B test, they don't mark you wrong, do they?
No, they won't mark you wrong whichever way you do it. They will mark you wrong if you did this.
If you carry it?
Yeah, if you actually put 2 to B here, because that's not right. You should have put Allen of 2 and Allen of B, because that's what they should change into. Right? So yeah, they will mark you wrong for that, definitely. So that's why I just say don't do it. Okay, when you do substitution, don't plug in your numbers. So, all right. Let me give you guys, so this again was just a why question, right? Why don't we carry upper and lower bounds? All right, so that was basically what that is. So that's not related to this section in a sense. I mean, I guess it could be, but it wasn't directly related to it. So homework, page 622, numbers 31 through 33, 35 through 40.